Section 7.2, Sum and Difference Identities. In this section, we're going to focus on deriving the sum and difference formulas and learning how to use them to verify other identities or simplify expressions. The hardest part of establishing the sum and difference formulas is to try to prove one of the possible sum and difference formulas. We're going to start off by proving the difference formula for cosine. That is, cosine of alpha minus beta equals cosine of alpha cosine of beta plus sine of alpha sine beta. What makes this verification a little bit more difficult is none of our previous properties involve using two angles at the same time. Instead, we're going to be a little bit more creative. Notice on the right, I have two figures drawn. In the top triangle, notice how I have angle alpha and angle beta drawn in standard position. From definition of our trig functions on the unit circle, angle alpha when drawn in standard position will correspond to the point cosine alpha sine alpha on the unit circle. Beta when drawn in standard position would correspond to the point cosine beta sine beta on the unit circle. From there, we can connect these points with a straight line. And we can see that the two terminal sides of alpha and beta, along with this straight line connecting cosine alpha sine alpha to cosine beta sine beta, forms a triangle. And the length of the angle opposite of this triangle is alpha minus beta. Through rotation of the triangle we have on the top, so that this side that I'm highlighting in green corresponds with the x-axis, we still have this side here opposite of the angle measuring alpha minus beta. Thanks to the fact that we're working with the unit circle, the third side, which we haven't highlighted yet, which I'm going to now in orange, will also correspond to each other. So what I'm working with is two congruent triangles. So whatever I get for the value of d in the first figure will also equal the same value of d in the second figure. How can I calculate the value of d? Recall the distance formula for college algebra. That is, the distance between any 2 points d equals the square root of the difference of the x component squared plus the difference of the y component squared. First, we'll apply the distance formula to our top figure triangle, and we're going to be finding the distance between the cosine alpha sine alpha point and the cosine beta sine beta point. And we get that our distance d will equal the square root of cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. Now we'll apply our formula to our bottom triangle and find the distance between the points 1, 0 and cosine alpha minus beta sine alpha minus beta, which is the point that corresponds to the angle alpha minus beta, which is drawn in standard position. And we get the square root of cosine alpha minus beta minus 1 squared plus sine alpha minus beta minus 0 squared. And remember, these two expressions will be equal because the length of d for both of the blue sides and both figures will be the same length. Since what's underneath the square roots is non-negative, we can get rid of the square roots from both sides of the equation. And with the square roots gone, we're going to then FOIL out our squared binomials. And with everything expanded, we have cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta on the left-hand side, while the right-hand side becomes cosine squared alpha minus beta minus 2 cosine alpha minus beta plus 1 plus sine squared alpha minus beta. From there, we notice that there's a lot of cosine squareds and sine squareds. That's going to allow us to use the Pythagorean identity. The cosine squared alpha plus sine squared alpha we know equals 1. The cosine squared beta plus sine squared beta also equals 1. The four terms that we have highlighted thanks to the Pythagorean identity will add up to 2. And the other two terms that we don't have highlighted will just bring down. So the left-hand side will simplify to 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Similarly, on the right-hand side, we see cosine squared of alpha minus beta, sine squared of alpha minus beta. So thanks to Pythagorean identity, they're going to sum to 1, and we already have a 1 present here. So those three terms will add up to 2, and we'll bring down the 2 cosine of alpha minus beta. Now we have a 2 on each side of the equation. They're going to cancel, and we now have negative 2 cosine alpha cosine beta minus 2 sine alpha sine beta equals negative 2 cosine alpha minus beta. Divide both sides by negative 2, and we have the identity we were trying to establish. Cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Now with the cosine of alpha minus beta identity established, we can quickly establish the cosine alpha plus beta property using even odd properties and the difference property. Now in the last section, usually we would pick the most complicated looking side, which visually looks like the right-hand side. But this time we're going to use the left-hand side to start, as we haven't seen many identities except for one that deals with the sum of two angles. However, the identity we just established has subtraction. So in order to set up for subtraction, we're going to change alpha plus beta to alpha minus negative beta. And then from there, we can apply our cosine alpha minus beta identity that we just established. And we get cosine alpha cosine negative beta plus sine alpha sine negative beta. Now we can use our already established even odd properties. Cosine is even, meaning the negative sign inside of cosine doesn't matter. Sine is odd, which means we can pull the negative sign outside of the sign. And we get cosine alpha cosine beta minus sine alpha sine beta, which is our right-hand side. This method of establishing one identity from a method that feels like it's coming out of the blue is usually a very common theme when trying to establish certain fundamental identities. But oftentimes, when one of these fundamental identities is established, the rest of the family does fall into place thanks to a whole variety of other properties. Another family of identities that we studied for right triangles was the cofunction identities. When we prove them with our right triangles, technically we only prove them for angles between 0 and 90 degrees. Here, we're going to establish the cofunction identities for all possible angles from negative infinity to infinity. This will also later help us establish the sum and difference properties for sine as well. We'll first establish that sine theta equals cosine of pi over 2 minus theta. We'll start with the left-hand side. With the left-hand side, we can apply the difference identity for cosine. We get cosine pi over 2 cosine theta plus sine pi over 2 sine theta. Cosine pi over 2 and sine pi over 2, we can evaluate. Cosine pi over 2 is 0, sine pi over 2 is 1. Anything times 0 is 0, anything times 1 is itself, and we're left with sine theta, which is our right-hand side. For the second identity, cosine theta equals sine of pi over 2 minus theta, we haven't established the sum difference rule for sine, but we can actually figure out this identity by doing a substitution for the first. If we use the substitution that theta equals pi over 2 minus u, our first identity on the top can be rewritten as sine pi over 2 minus u equals cosine pi over 2 minus the quantity pi over 2 minus u. Inside of the cosine, distribute in the negative sign, pi's over 2 cancel, we're left with cosine u. Now, even though I have that sine pi over 2 minus u equals cosine u, the letter doesn't matter. I can replace u with any letter or variable I wish. So the second identity does also hold true. To establish the tangent and cotangent cofunction identities, we can use the cofunction identities we just established in combination to the quotient identities. And for the secant and cosecant cofunction identities, they can be established using the first two cofunction identities we already established, along with the reciprocal identities. I'll leave that as an exercise for you to try to establish the other four cofunction identities. Now we're going to complete the list of sum and difference formulas. We already have the sum and difference formulas for cosine that we've established on the previous slides. Now we're going to come up with sum and difference formulas for sine and tangent. Let's start with the difference formula for sine. We'll start with our left-hand side of sine of alpha minus beta. Thanks to our work with cosine, we already have the sum and difference formulas for cosine established. So we're going to rewrite our sine of alpha minus beta in terms of cosine using the cofunction identities. So we get that sine of alpha minus beta equals cosine of pi minus the quantity alpha minus beta, which if we distribute in -1, we get cosine of pi over 2 minus alpha plus beta. In order to use our identity for cosine, we're going to group pi over 2 minus alpha as a single angle. The reason why I want to use pi over 2 minus alpha in my group is my cofunction identities do involve pi over 2 minus an angle. So here I see pi over 2 minus an angle. That looks like the best choice. So from here, I can apply the sum rule, and we have cosine pi over 2 minus alpha times cosine beta minus sine pi over 2 minus alpha sine beta. But cosine pi over 2 minus alpha, sine pi over 2 minus alpha will allow us to apply the cofunction identities again. Cosine pi over 2 minus alpha will become sine alpha. Sine pi over 2 minus alpha will become cosine alpha. And from there, we have sine alpha cosine beta minus cosine alpha sine beta, which is our right-hand side. The sum formula for sine can be proven exactly the same way as we proved the sum formula for cosine, just by using the even-odd properties. Now we're going to establish the sum and difference formulas for tangent. We'll start with the sum formula for tangent. The difference formula will just come as a direct result of the even-odd properties, just like what we did for cosine. So I'll leave the difference as an exercise. So we'll start with the left-hand side. Now we already have sum rules established for cosine and sine. So we'll use the quotient identity to rewrite our tangent of alpha plus beta in terms of sine and cosine. Then we can apply the respective sum rules to sine alpha plus beta and cosine alpha plus beta. Now that we've rewritten our sine of alpha plus beta and cosine of alpha plus beta, let's look to the right-hand side of our sum formula for tangent for inspiration on what to do next. Notice in the denominator, the first term is 1, and it's 1 minus something. So we're going to want to make this cosine of alpha cosine beta into 1. We can do that by multiplying our denominator by cosine. We can do that by multiplying the denominator by 1 over cosine alpha cosine beta. And what I do to the bottom, I also have to do to the top. Now we can distribute. When we distribute into the numerator, notice in the first term, we'll distribute into the numerator and the denominators. We'll go ahead and distribute the 1 over cosine alpha cosine beta into the numerator and denominator. And it looks like we might have created a mess after distributing. But notice we're going to have a lot of terms cancel. For instance, the cosine beta in the top first term, cosine alpha is in the top second term, and the entirety of the first bottom term cancel out. Next, also notice how we have a lot of sines over cosine. We have sine alpha over cosine alpha, sine beta over cosine beta, and a sine alpha over cosine alpha with a sine beta over cosine beta. So after canceling and using the quotient identity, our first term in the numerator becomes tangent alpha. Our second term in the numerator becomes tangent beta. In the denominator, our first term becomes 1. And in our second term in the denominator, we have tangent alpha times tangent beta, which is the right-hand side of our sum formula, for tangent. Our difference formula of tangent can also be proven through this exact same methodology, or you can apply the even-odd properties, just like what we did, to establish the second formula for sine or cosine. One of the uses for the sum and difference identities is that it will allow us to find the exact value of trig functions at angles that we usually wouldn't find on the unit circle. For example, cosine of 105 degrees. 105 degrees is not a value we would find on the unit circle, but we can figure out two angles who have a sum of 105 degrees that we can find on the unit circle. that would be 60 degrees and 45 degrees. So cosine of 105 degrees is equal to cosine of 60 degrees plus 45 degrees. Now to find the exact value, we can apply the sum identity of cosine, and we get cosine of 60 degrees, cosine 45 degrees, minus sine 60 degrees, sine 45 degrees. 60 degrees and 45 degrees we can find on the unit circle. So by evaluating all four of our trig functions at the angles given, we obtain 1/2 times root 2 over 2 minus root 3 over 2 times root 2 over 2. Then by following order of operations, and we get that cosine of 105 degrees equals root 2 minus root 6 all over 4. Now we're going to find the exact value of sine of pi over 12. Just like with 105 degrees, pi over 12 is not an angle that is available on the unit circle. And notice that pi over 12 is really small. So I want to try to think of two angles on the unit circle that if I subtract them, I'll get a difference of pi over 12. Well, pi over 4 minus pi over 6 is pi over 12. So we can use pi over 4 and pi over 6 to help us evaluate sine of pi over 12. Keep in mind that there are several angles that could have been picked. Pi over 4 minus pi over 6 is not the only way to find angles who have a difference of pi over 12. Now we can apply the sine difference formula. And when we do, we have sine pi over 4 cosine pi over 6 minus cosine pi over 4 sine pi over 6 equals sine pi over 12. Now we can evaluate each trig function at the angles that we know are on the unit circle. And we get root 2 over 2 times root 3 over 2 minus root 2 over 2 times 1/2. Following the order of operations to further simplify, and we get that the exact value of sine pi over 12 is root 6 minus root 2 all over 4. Now we're going to evaluate secant of pi over 4 minus pi over 6. Now here we know what two angles we're subtracting, but the problem that we have now is we don't have a sum difference formula for secant. We only have sum difference formulas for sine, cosine, and tangent. But recall that secant and cosine are reciprocals. So secant of 5 pi over 4 minus pi over 6 equals 1 over cosine 5 pi over 4 minus pi over 6. Down below, we're going to find the exact value of the cosine of 5 pi over 4 minus pi over 6. To do this, we'll apply the difference formula for cosine. And when we apply the difference formula of cosine, we get cosine 5 pi over 4 cosine pi over 6 plus sine 5 pi over 4 sine pi over 6. Now we can evaluate each trig function using our unit circle, and we get negative root 2 over 2 times root 3 over 2 plus negative root 2 over 2 times 1/2. Then apply order of operations, and we get negative root 6 minus root 2 all over 4. Since we know the exact value of cosine 5 pi over 4 minus pi over 6, the reciprocal of our answer will be the value of secant 5 pi over 4 minus pi over 6. The reciprocal of negative root 6 minus root 2 over 2 over 4 will be 4 over negative root 6 minus root 2. From there, we can rationalize by multiplying the numerator and denominator by the conjugate of the denominator, which would be negative root 6 plus 2. In the top, in case we need to simplify, we'll keep that factored. In the bottom, we can FOIL, and when we FOIL, we'll get 6 minus 2. 6 minus 2 is 4, so the 4 in the denominator will cancel with the 4 in the numerator, giving us negative root 6 plus root 2 as the exact value of secant, negative 5 pi over 4 minus pi over 6. Now we're going to find the exact value of tangent pi over 6 plus pi over 4. Unlike the last example, we do have a sum formula for tangent. So we'll go ahead and apply the sum formula. And when we do, we get tangent pi over 6 plus tangent pi over 4 all over 1 minus tangent pi over 6 times tangent pi over 4. From there, we can evaluate tangent at each of these angles. And we get that tangent pi over 6 is root 3 over 3, while tangent pi over 4 is 1. In the denominator, we can multiply to clean up a little. Anything times 1 is itself. Since we have complex fractions, we can multiply numerator and denominator by the least common denominator of all of our fractions, which is 3. And when we distribute the 3, we get root 3 plus 3 all over 3 minus root 3. Just like before, we do want to rationalize the denominator, so we'll multiply top and bottom by 3 plus root 3. This time in the numerator, I am going to FOIL. When we FOIL the numerator, we get 3 plus 3 root 3 plus 3 root 3 plus 9. In the denominator, we get 9 minus 3, which gives us 12 plus 6 root 3. Divide each term by 6, and we get 2 plus root 3 as the exact value of tangent pi over 6 plus pi over 4. Now we're going to find the exact value of the following. Sine of cosine inverse of 1/2 plus sine inverse of 3 over 5. Here, our input is two inverse trig functions. And notice how they're being added together inside a sine. In order to try to simplify this farther, we should apply the sum formula for sine. And when we do, we get sine of cosine inverse of 1/2 times cosine of sine inverse of 3 over 5 plus cosine of cosine inverse of 1/2 times sine of sine inverse of 3 over 5. From there, if we look closely at the second term, since 1/2 and 3/5 are between negative 1 and 1, the cosine and cosine inverse and the sine and sine inverse will cancel out, leaving us with 1/2 times 3/5. The problem is the sine of cosine inverse and the cosine of sine inverse. Now, the sine of cosine inverse of 1/2 we could evaluate through brute force computation, since 1/2 is a value that we commonly see as the answer for sine. However, we want to be able to do that for sine inverse of 3 over 5. 3 over 5 is not a value we commonly see from the unit circle. Let's say we didn't recognize 1/2 as a common value we could see on the unit circle, or we didn't have a unit circle with us. We can still figure out the value of these compositions by using triangles. Our triangle for cosine inverse of 1/2 I'll put in green, and the one for sine inverse of 3 over 5 will be in orange. I do need to make two separate triangles since cosine inverse of 1/2 and sine inverse of 3 over 5 are most likely different values and do not add up to 90 degrees, so they may not fit in the same triangle. The definition of cosine with right triangles is adjacent over hypotenuse, so we'll make one the adjacent side to the hypotenuse, which means we need the opposite side from Pythagorean theorem. we get that the opposite side is root 3. In the orange triangle, the definition of sine is opposite over hypotenuse, so we'll make the opposite 3, the hypotenuse 5, and we use Pythagorean theorem for the adjacent, and we get 4. Now we can evaluate the sine of cosine inverse of 1/2 using the green triangle. Sine is opposite, which is root 3, over hypotenuse, which is 2, which is the value we would expect from the unit circle. The cosine of sine inverse of 3 over 5 would be adjacent 4 over hypotenuse 5. Now we can follow order of operations and simplify, and we get that our final answer is 4 root 3 plus 3 all over 10. Now we're going to find the exact value of cosine inverse of 4x plus sine inverse of 3y. In this problem, we're going to assume that the variables are in the proper interval that's going to cause our cosine inverse and sine inverse to be defined. Just like in the last problem, we're going to start off by using our sum property for cosine. And when we do, we get cosine of cosine inverse of 4x times cosine sine inverse of 3y minus sine of cosine inverse of 4x times sine of sine inverse of 3y. Since we're assuming x and y are in the intervals that are going to cause our inverse trig functions to be defined, we will apply the cancellation properties. The sine and sine inverse will cancel. The cosine and cosine inverse will cancel. As for the other two, we should draw two separate triangles to evaluate each one. In green, we'll draw a triangle for sine inverse of 3y. In orange, we'll draw the triangle for cosine inverse of 4x. We'll put the angles in the bottom left like usual. Sine is opposite over hypotenuse. Since our input to sine inverse is 3y, we'll make the opposite 3y the hypotenuse 1. We'll use Pythagorean theorem to find the adjacent side in the green triangle, and we get the square root of 1 minus 9y squared. For the orange triangle, cosine is adjacent over hypotenuse. Since 4x is the input of cosine inverse, we'll make the adjacent side 4x, the hypotenuse 1. Then through Pythagorean theorem, we get that our opposite side is the square root of 1 minus 16x squared. Now we have everything we need to evaluate our compositions. The first was 4x, thanks to the cancellation. The second, thanks to the green triangle, will be adjacent over hypotenuse, which will be square root of 1 minus 9y squared. The sine of cosine inverse of 4x, thanks to the orange triangle, is square root of 1 minus 16x squared. And the sine of sine inverse of 3y is just 3y. Now from there, we can just rewrite the order, clean things up a little bit, and we get 4x times the square root of 1 minus 9y squared minus 3y times the square root of 1 minus 16x squared as our final answer. Now, given that sine alpha equals negative 3 over 5, with alpha being between 3 pi over 2 and 2 pi, along with cosine beta equaling to 12 over 13, with beta between 0 and pi over 2, we're going to start off by finding sine of alpha plus beta and cosine of alpha minus beta. First, if we take a look at both formulas for sine of alpha plus beta and cosine of alpha minus beta, we see that both identities depend on the value of sine alpha, sine beta, and cosine beta. So far from the given information, we know sine alpha, we know cosine beta, but we're missing cosine alpha and sine beta. How can we figure out the value of cosine alpha and sine beta in order for us to evaluate sine of alpha plus beta and cosine of alpha minus beta? Well, if we think about the fact that we're given that sine alpha is negative 3 over 5, and we know alpha is between 3 pi over 2 and 2 pi, which is in quadrant 4, we can use the Pythagorean identity to help us to figure out cosine alpha. From the Pythagorean identity, we have that cosine squared alpha plus sine squared alpha equals 1, and while we're at it, cosine squared beta plus sine squared beta also equals 1. Now, just like in our past exercises, we can plug in our known quantities for sine alpha and cosine beta and solve for the other trig function. And after plugging in and manipulating, we get that cosine alpha is positive or negative 4 over 5, while sine beta is positive or negative 5 over 3. But keep in mind, we know what quadrant alpha and beta are. As discussed earlier, we know alpha is in quadrant 4. Cosine is positive in quadrant 4. So cosine alpha is positive 4/5. Beta we know is between 0 and pi over 2, which is quadrant 1. Sine is positive in quadrant 1, so sine beta is positive 15 over 3. Now we have everything we need to figure out sine of alpha plus beta and cosine of alpha minus beta. Plug our values into our formulas. Sine alpha is negative 3 over 5. Cosine beta is 12 over 13. Cosine alpha is 4/5, and sine beta is 5 over 13. And when we do the arithmetic, we get negative 16 over 65. Now we'll repeat the same thing for cosine of alpha minus beta. And when we plug in our values, we get 4/5 times 12/13 plus negative 3/5 times 5/13, which is equal to 33 over 65. Next, we're going to figure out the value of tangent of alpha plus beta and tangent of alpha minus beta. First, let's take a look at the formulas for the sum and difference for tangent. And notice that the sum and difference formulas for tangent require tangent of alpha and tangent of beta. So far, we only know sine of alpha, cosine of alpha, sine of beta, and cosine of beta. But thanks to the quotient identities, we can easily figure out tangent of alpha and tangent of beta. Tangent of alpha from our quotient identities will be sine alpha, which is negative 3/5, over cosine alpha, which is 4/5, which is equal to negative 3/4. Tangent beta is sine beta, which is 5/13, divided by cosine beta, which is 12/13, which is 5/12. Now that we have tangent alpha and tangent beta, we can plug those values into the formulas, and then we can do the arithmetic. For the tangent alpha plus beta, we get negative 16 over 63. For the tangent alpha minus beta, you get negative 56 over 33. Now we're going to practice using the sum difference formulas to verify the following identities. We're going to start with sine of x minus y over cosine x cosine y equals tangent x minus tangent y. Here, we're going to start off with the left-hand side, since the left-hand side looks the most complicated. If we look at the right-hand side, notice that we only have x and y as the inputs to the trig function. But if we look at the sine of x minus y, that has a distinct input compared to the others. So we're going to use the sum and difference identities to help rewrite the sine of x minus y. And when we do, the numerator becomes sine x cosine y minus cosine x sine y. Now, if we look at the right-hand side, notice that it's a two-term expression. Right now, our left-hand side is currently a fraction, but the numerator is two terms. So what we'll do is we will divide each term in the numerator by our denominator. And when we do, we can see the cosine y's cancel in the first term and cosine x's cancel in the second term. Now, from our right-hand side, we know we want tangent in our expression. And in what we have so far in our simplified left-hand side, we have sine x over cosine x, which is tangent x through the quotient identities, and sine y over cosine y, which is tangent y by the quotient identities, which is our right-hand side. Next, we're going to verify that sine of x plus y plus sine of x minus y equals 2 sine of x cosine y. Our left-hand side, we can tell is the most complicated, so we'll start with the left-hand side. Just like before, I do see the sum of angles as the input of my sine functions, so we can apply the sum and difference identities for sine. Sine of x plus y will become sine of x cosine of y plus cosine of x sine of y, while sine of x minus y becomes sine of x cosine y minus cosine of x sine of y. The cosine x sine of y terms will cancel, and we can collect our sine x cosine y terms. We get 2 sine of x cosine y, which is equal to our right-hand side.